Why GPUs may need light. Here's the real reason it matters. Big question. Why do copper links hit a wall? And how can optics change the game? Most people blame the obvious part, but they miss the real gate. Today we follow the cue, not the hype. Signature segment later, copper versus light sprint, the photon race. Disclosure: AI-generated educational recreations. No brands. No real dashboards. ProcessVerse rules. Layer A works today. Layer B is next. And every claim gets a tag. Verified, depends, or unknown. Because modern tech is a chain of gates. Where a gate narrows, a queue forms. Fix the wrong gate, nothing changes. Fix the right one, everything feels smoother. Visuals will move fast, 5-10 seconds each. Real-world props, clean visualizations, UI-style icons. No buzzwords without a mechanism, no single metric worship. Today we score 8 categories. Each one explains where copper slows and where optics begins to matter. Then, the mid-episode reveal, and a 1-minute checklist you can reuse for any system. Remember, the bottleneck moves. Okay, scoreboard starts now. Bandwidth isn't the headline number. It's how much bandwidth fits per millimeter of edge. What matters? Copper lanes need spacing. Electrical crosstalk demands physical distance. Optical waveguides? They can be packed tighter because photons don't short-circuit each other. But here's the trap. More lanes is not equal to instant wins. You still need modulators, drivers, couplers. Bandwidth density only matters if your packaging can actually feed it. Tag. Verified. Copper's edge density hits physical limits. Trade-off. Adding more electrical lanes increases heat per mm. Takeaway. Bandwidth density is a gate that shrinks with every GPU generation. Power per bit explains why large clusters burn megawatts. What matters? Electrical signaling burns energy pushing electrons against resistance and capacitance. Optics moves photons. No charge, no RC delay, no resistive losses. The trap. People think optics is free power. No modulators and lasers cost energy. But electrical SERDES scales brutally. Higher speed demands exponential power. Tag. Verified. Optics has better scaling at extreme speeds. Trade-off. Optical components add alignment, overhead, and thermal sensitivity. Takeaway. Power per bit decides the cluster's electric bill. Latency is where copper secretly loses. What matters? Electrical signals slow down as wires get longer. Propagation speed, half the speed of light. Optical fiber, to 70% speed of light with much lower distortion. The trap, lower latency doesn't matter unless the compute pipeline depends on it. Training with huge batches? Maybe not critical. Inference with micro batches? It's everything. Tag. Depends. Latency wins vary by workload. Trade-off. Optical modulators can add fixed overhead, especially if conversion isn't co-packaged yet. Takeaway. Latency is the quietest bottleneck and the easiest to overlook. Thermals decide who throttles first. What matters? Copper SERDES heat up as signaling speeds increase. Optics moves heat to lasers and drivers, often easier to cool. The trap. You still need thermal coupling to keep modulators stable. Optical links remove electrical heat, but introduce photonic heat budgets. Tag. Verified. High-speed copper burns watts per link. Takeaway. Thermals are a system-wide budget, not a component problem. Packaging is where optics gets real, and real complicated. What matters? To win, optics must be co-packaged, next to the switch or GPU. Longer electrical stubs erase optical advantages. The trap. People think you just plug in fiber. No co-packaging requires alignment precision in micrometers. Trade-off. Optics wins density, but copper wins simplicity. Tag. Verified. Packaging limits adoption speed more than physics. Takeaway. Optics only wins when packaging becomes part of the compute architecture. Reliability is not optional at hyperscale. What matters? Copper is robust. It bends, flexes, tolerates movement. Optics, dust, misalignment, connector wear, small factors turn into big outages. The trap. People assume optics equals perfect, but lasers degrade, and temperature drift changes behavior. Tag. Depends. Optical reliability improves fast, but field variation is real. Takeaway. Reliability is a gate that optics must earn over time. Cost determines rollout speed. What matters? Copper is cheap, mature, everywhere. Optical transceivers, complex, temperature stabilized, with packaging that requires new factories. The trap. Cost curves drop with scale, but scale requires demand. Tag. Unknown. When optics becomes cheap enough, depends on manufacturing and adoption. Takeaway. Cost is not the enemy. It's a governor on timelines. Roadmap is staged, not instant. Layer A today. Electrical I. O dominates, but burns power per bit. Layer B next. Co-packaged optics reduce distance and remove electrical bottlenecks. Layer C. Later. All optical fabrics. If modulators and lasers reach chip-scale integration. Tag. Unknown. Timelines shift with yield and packaging breakthroughs. Takeaway. Optical migration is a curve, not a flip. Here's the twist, the one most people miss. Optics can win bandwidth and still lose the race, because packaging becomes the new gate. You widen the optical link, but the attachment point, the connector, the coupling region, the assembly, becomes the queue. So migration is staged, not instant. The right question isn't, which is faster? It's, where is my system waiting? This is why the same upgrade feels amazing for one team and pointless for another. Bottleneck hunting is a loop, find, fix, retest. Because the queue relocates. If you don't retest, you're just upgrading noise. This loop is how every high-efficiency AI team makes decisions. Step 1. Name the gate. Where exactly is the waiting happening? Step 2. Pick the cheapest lever that opens that gate. Step 3. Change one variable only. Step 4. Measure again, with the same test. Step 5. Expect the bottleneck to move. If it moved, repeat the loop. Layer A first, layer B after. Don't buy the future until your present is clean. If you learn one new thing, this series is for you. Replay the retention chapter if you want the intuition fast. Vote with your click on the end screen. Comment your use case, training, inference, or infrastructure. No hype, only systems. End screen in 3, 2, 1. Pick a tile. Go. Quiet reminder. If you can't see the queue, build a test that reveals it. Don't trust peaks. Trust sustained flow. When you understand the gates, you control outcomes. That's the point of ProcessVerse. End screen now.
verify these claims using our two-layer scoreboard. While Layer A works today, we must consider the trade-offs.